everyone. I am Sindhu from ECH section. I am going to present my project on CRC 16 based error detection using LFSR for data integrity. The application we have considered for this project is an electronic voting machine. In voting system, maintaining accuracy and reliability is very important because even a small error can affect the final election result. In our project, whenever a voter casts a vote, the data is first taken as an input and then processed using the CR16 algorithm. Instead of sending the data directly, we generate CRC bits using a linear feedback shift register or LFSR and append these bits to the original data. This encoded data is then transmitted through a communication channel. However, during transmission, noise or external disturbances may introduce errors into the data. At the receiver side, the same CRC16 process is applied again to the received data. The system recalculates the CRC and compares it with the received CRC bits. If both values match, it means the data is correct and error-free. If they do not match, the system detects an error and the error signal becomes high. Additionally, our design is capable of detecting different types of errors such as single bit errors and burst errors, which make the system more reliable. By using CRC16 with LFSR, our project ensures secure and accurate data transmission, which is especially important in applications like electronic voting machines where data integrity is critical.
Elections are the foundation of democracy, and every vote must be secure, accurate, and reliable. This project presents CRC, 16-based error detection in electronic voting machines, using LFSR for data integrity verification to ensure secure, reliable, and accurate voting systems. CRC 16 ensures the integrity and security of vote data inside electronic voting machines. It detects errors using a 16 BIT cyclic redundancy checked during data transmission. At the same time, LFSR encodes the data to protect it from tampering. This ensures accurate election results and reliable, secure electronic voting.
In this project, we implemented CRC16 based error detection using Verilog to ensure data integrity in applications like electronic voting machine. First, the CRC generator module takes 8-bit input data and generates a 16-bit CRC using the polynomial. It performs XOR and shifting operations to reduce the higher CRC value. Next, at the receiver side, the CRC checker recalculates the CRC from this received data and compares it with the transmitted CRC. If both match, the data is correct. Otherwise, an error is detected. The top module connects these blocks to simulate data transmission and verification. Finally, the test bench demonstrates different cases like no error, single bit error, and burst error, providing that CRC16 can effectively detect data corruption. After simulation, this is the waveform update. Here we can observe the input code data, the received data, and the error signal.
The simulation waveform shows the operation of the CRC-based error detection system implemented in Verilog and simulated using Xilinx Vivado. In the waveform, vote data represents the transmitted 8-bit data, while corrupted data represents the received data at the receiver side. The error signal indicates whether any transmission error has been detected. At the initial time interval, the transmitted data CC matches the received data CC, so the error signal remains 0, indicating that the transmission is correct and no error is present. Later in the simulation, the received data changes from CC to CD, while the transmitted data remains CC. This mismatch causes the error signal to become 1, indicating that the CRC mechanism has detected an error in the received data. Further changes in the received data, such as CF and F7, also differ from the transmitted data, so the error signal continues to stay 1, confirming that the system successfully identifies data corruption. Overall, the waveform demonstrates the CRC-based design correctly detects mismatches between transmitted and received data, thereby ensuring data integrity during communication.
This slide shows how CRC 16 detects errors in electronic voting machines. First, the vote data is entered into the EVM as digital information. Next, the data is encoded using LFSR, which prepares it for secure transmission. Then, The CRC16 generator calculates a checksum using a predefined polynomial. Finally, at the receiver side, the calculated CRC is compared with the received value to verify the data integrity. If both match, the data is correct. If not, an error is detected. LFSR, or Linear Feedback Shift Register, is used to enhance data security. It generates a pseudo-random bit stream to scramble the vote data. This protects the data from tampering during transmission. By using XOR operations, LFSR encodes the data before CRC16 processing, making the system more secure. CRC16 provides multiple benefits for electronic voting systems. It detects and flags errors in vote data, ensuring accuracy. It enhances security by making data harder to intercept or alter. It also improves voter confidence by maintaining trust in the system. Finally, it ensures reliable and accurate recording of votes. In conclusion, CRC16 and LFSR together enhance the security and reliability of electronic voting machines. By combining data scrambling and error detection, they prevent tampering and ensure data integrity. This trusted technology helps maintain fairness and accuracy in the electoral process. Thank you for watching. Remember, voting security is crucial. To summarize, this system ensures voting security, uses LFSR for data protection, and CRC16 for accurate error detection. Together, it builds trust and reliability in electronic voting systems. Thank you for your attention. Let's make every vote count.